Welcome to a lesson with Dr. Powell. Let's talk about this vector of areal projections, dyz, dzx, and dx dy. The magnitude of this turns out to be the actual area that we're interested in of the little parallelogram. So this parallelogram right here has areal projections. This is the areal projection onto the YZ plane. This is the areal projection onto the ZX plane. This is the areal projection onto the XY plane. Now the actual area of the parallelogram turns out to be the magnitude of this vector of areal projections. Why is that? Let's talk about that. First of all, let's take this little piece of the surface, think of it as a flat parallelogram. If we're up close, we can think of it like that, as sitting in its tangent plane of the surface itself. And let's think of creating a volume function, where the input of the volume function is a vector, where we think of the standard coordinates or in standard position of the vectors in x, y, z, so that the volume function becomes a function of three coordinates, x, y, and z. So we start from the base of the parallelogram and we take an input vector. Suppose that we inputted maybe a vector that's facing in this direction. Then what we would do is we would kind of take that vector and translate it in all the different ways we can and form a parallelepiped out of this and take the volume of that, and that would be the output of this function, of output of this. Now this function itself actually ends up being linear, meaning that the approximation that we get from the derivative, so derivative times run equals rise, actually ends up being exact. So the approximation of the derivative is exact. That's what linear means. So that means that if we were to take the gradient Vx, Vy, Vz, and then dot it with, and then dot it with the run, so kind of which are the actual coordinates here, x, y, z. If we're going from 0, notice the volume right at 0. If the vector's at 0, it's just 0 of the whole thing. So if we go up here, actually, this function is nothing more than this, where x, y, z is simply the coordinates of a vector that is written in standard form, that is, at that particular place. So we end up getting some kind of function that looks like this. This is the volume function. Now, a level surface for this volume function happens in the tangent plane itself, because any vector that lies in the tangent plane will give a volume of 0. So that is a level surface. That means that the gradient itself is orthogonal to the parallelogram itself. So we have actually this gradient here, which we'll call maybe the gradient of V, happens to be orthogonal. Now, something else we know. What if we were to input into this function for volume that's based off of this parallelogram as a base, a unit vector? So a unit vector coming up. Now we put a unit vector here and we dot it with this. Dotting with the unit vector that's orthogonal, so in the same line, basically amounts to projecting this guy onto itself. Since dot product with unit vector is projection, and if we're projecting on the same direction as this, we end up getting just projection onto itself, which means that if this is a unit vector that's parallel to this one, also orthogonal, we end up just getting the magnitude. So the volume is actually going to be equal to itself the magnitude of the gradient. And partly because the gradient happens to be orthogonal, and that's how we're computing the actual volume. And so if we stick a unit vector in here, the magnitude here will be, the magnitude of this will actually be the volume if we use a unit vector. But see what happens when we use a unit vector here as well to find the volume. So when you use a unit vector, we actually get that this magnitude is the volume. Interesting, but we also get something else. We use a unit vector that's orthogonal, getting like a rectangular type shape and perpendicular, and the volume that we actually get is actually equal numerically to the area of the base, since area times height, and the height orthogonally right here is just 1 times base is volume, but the base is area, so area times 1 is volume, so area numerically is equal to volume. So that means the magnitude of this guy is actually equal to the area of the parallelogram. Great. But how do we think about these guys? This Vx, this Vy, this Vz. These actually turn out to be precisely these aerial projections. Let's talk about why. So let's just think two-dimensionally for a minute. What if we have a parallelogram like this, and suppose it's and think about, and that's a base, say, and think about how we compute it, the area of it. We take the base times the height, right? So think about the height as being a direction. So it's always base times height. So if base is constant, say, and height is what's variable, like you're in this direction, what's the derivative with respect to height, with respect to this direction? Isn't it just the base? So we're using that idea. We just beef up that idea and think of this base as being the aerial projection. So indeed, this ends up being the aerial projection. The aerial projection, the aerial projection. So if you just simply take the different aerial projections, 1, 2, and 3, find the magnitude, you get the area of the parallelogram. We'll be using this idea. Thanks for watching.